It's always good to remember today, December 7th, is the 75th anniversary of the bombing of Pearl Harbor. In fact, when we get out of class, that would be the time when the bombing occurred. I see that I'm no longer broadcasting my screen to them, but that should be, there you go. So they have it back. Things that are, kind of historical, like good to keep in mind. That attack, of course, brought the United States into the war. The United States was clearly allied against Japan, but we weren't a participant. We were supplying munitions, making a lot of money, supplying food and armor to the Allied side. And so the Japanese actually, by and large, don't consider it an act of war attacking us because they consider we were already in the war. So I dated a Japanese girl. First of all, she was like, what's special about December 7th? It was December 8th when we attacked you, because of the time difference. And second of all, she was, you were already opposed to us. We were just attacking our enemy in the war, was her opinion. But Prime Minister Shinzo Abe is actually going to go visit Pearl Harbor, the first time a Japanese premier has ever done that, later on this month. That's a big step politically, acknowledging, yes, we did attack Pearl Harbor, just like President Obama was the first president to visit Hiroshima this past May, acknowledging, yeah, we did some pretty devastatingly bad things here. So it's kind of good to see the countries at least try to play nice together. And we only can hope that happens in the future. Okay, I am going to cover, actually I think it's 12 slides of material that I did get done last class period, talking about primarily the loudness of sound, what the decibel is, and how that works. So I ended with this slide here that shows our hearing. And notice on this side, it has sound level in units of dB. dB is short for decibel. Deci. What deci is a prefix? What does deci mean? Tenth. So decibels are actually tenths of bells. We very often just lose that and think that the decibel is the unit, but it's actually the bell, and the decibel is the tenth of a bell. And so the decibels, 0 is what we consider the threshold for hearing. But as you can see, somebody with standard hearing can hear sounds that are below 0 decibels if you're near the 4,000 hertz range where we hear the best. And if you have something that's in the range where my voice is somewhere in this ballpark. If I was speaking at 0 decibels, nobody would hear me, even if they had what we consider perfect hearing. It would have to be quite a bit louder for you to hear. So how loud am I speaking? It's somewhere in the ballpark of 70 to 80 decibels is the level of a teacher teaching. A conversation would be more like 70 decibels. So we're going to try to understand that before we're done today. So one of two clicker questions. Oh, shoot. Give me a second. I'm actually going to reset this while we're waiting. While you're waiting. Excellent. I thought I had this already, but I have to do two things. Now it's ready. Okay, you can start answering now. Paris, you were the first one in, just in case you're, probably sitting there going, gonna be there. Okay, what frequency do humans typically hear the best? Okay, I'll give about 5 more seconds here. All right. So what we ended up with was 2, 3, 40, and 1. A pretty strong agreement on 4,000 hertz. Why? Well, I hope it's because you noticed right here, yes, that goes the lowest. It has that dip at about 4,000 hertz. We can hear the best there. Now, not everyone has the same hearing. You probably know sometimes I don't hear what you guys say when I really should. We have our ears that are our hearing elements, and this not being a biology class, I'm not going to spend as much time as I usually do here. But things to note are that number one, you have the outer ear. The outer ear takes sound energy and filters it into a smaller region. Since intensity is the energy per time per unit area, if you take that energy and bring it to a smaller area, what does that do to the intensity? It increases it. So by having the outer ear funnel sound in, we increase the intensity just by condensing the sound to a smaller region. So that's the first part of amplification. Second part is a mechanical, the anvil and stirrup. You have the eardrum that will oscillate when you have higher pressure on the outside. It pushes it in. Lower pressure on the outside, it comes back out. I have had one of my eardrums ruptured, which is not the best thing in the world because now I have scar tissue in my eardrum. Makes it not work as well. The stirrup and anvil system is essentially a lever that once again gives you a mechanical advantage that makes it so a small motion over here results in a bigger motion over here, amplifying the sound. And then you have the, what is it called, the cochlea? Yeah, cochlea, there it is. The cochlea that has a canal, the sound goes through, has a little cilia that will vibrate with the vibrations, and it's those vibrations of the cilia then are turned into electrical impulses that we hear. And so you can have things like, if you have those little cilia start to get stiff, then your hearing will decrease, especially in the high frequencies, because when they get stiff, they don't vibrate as easily at the high frequencies. So here's some graphs just illustrating typical hearing problems. The top one is showing hearing that is pretty standard. That is compared to the threshold for hearing that we saw in the first graph. You saw that it went down, so it was the most acute at 4,000 hertz. But compared to that, this person's hearing is pretty much exactly on. They're a little bit better than average in the left ear, but pretty much right on average with the right ear. This one here, I think they call it a dog bite hearing loss because of having some loud sound event. That's what my hearing is like. I was surprised that mine wasn't the lowest one. This one here is old age. With old age, you lose those higher frequencies. And I thought I must be just losing higher frequencies. But no, I lost the middle frequencies. I attribute it to mowing the lawn for years with no muffler on my lawnmower. That thing was loud, and I just well, whatever. Not smart. So, you can have different kinds of hearing loss. You don't want to have any hearing loss. That's why if you go to a music concert, the wise person does what the musicians are doing and puts earplugs in because the loud, it's going to be pretty loud and it can be damaging to your hearing. And if you shoot a gun, yes, make sure you wear protection. Wasn't me. The perceived loudness, how loud we sense something to be, depends on the intensity, the amplitude of the sound wave, but it's not linear. It's roughly proportional to the logarithm. So when we talk about the decibels are based on a logarithmic measurement of the intensity. And I'm just going to move, here we have just one important piece of information. We consider the threshold of hearing to be 10 to the minus 12 watts per meter squared. That's the intensity for the threshold of hearing. As we saw, obviously the threshold for hearing has a different intensity depending on the frequency, but this is what we use as our standard for the decibel. And so then we measure the ratio of the intensity of a sound to that threshold, and that gives us something that tells us about the ratio of intensity, and then we take the log of that. So the log base 10 of I over I0 is equal to the sound intensity level in bells. So it's just the log base 10 of the ratio of intensities. But of course, what's the standard thing we say? We don't say bells, we say decibels. And so the decibels means that we're going to multiply by 10, move the decimal place 1, to make it decibels, which we just use the symbol dB for And I'm going to put the capital on the bell. Obviously, we never put the capital on the bell. And so that's how we get the sound intensity level. We just take that ratio. And it's not that hard. Look at the example I gave you. If you have a sound that's 10 to the minus 5 watts per meter squared for its intensity, you take that, you divide by 10 to the minus 12. When you divide something with exponents, as long as it's the same number with exponents, you just subtract the exponents. So I'm going to have 10 to the minus 5 divided by 10 to the minus 12 is 10 raised to the parenthesis minus 5. That's a 5. Minus 12. That 5 is so non-readable. And minus 5 minus a negative 12 is 7. So that's equal to 10 to the 7th. And then what is the whole function of a log? What does a log do? Rachel, weren't you the one talking about this earlier? I thought it was you. Not today, but like a month ago. No. My math teacher always said, okay, the function, the log base 10 is saying what power do I have to raise 10 to get this number? And so if I have the log base 10 of 10 to the 7th, that's saying what power do I have to raise 10 to get 10 to the 7th? That's kind of a silly question, right? What power do I raise 10 to get 10 to the 7th? 7, right? It's not hard at all to do a basic log in your head. Now, if it was, 3.5 times 10 to the 7th, I would have 7 point something, and the decimal would come from the 3.5 stuff. So this here gives me a sound intensity level of log base 10 of 10 to the 7th is 7, multiplied by 10 to get to decibels, so it would be 70 decibels. Beta is the symbol we use for the sound intensity level. So that's how we calculate a decibel. Now, before I go to the next slide, if you buy a more expensive tuner or receiver, so like at home for my TV, I have a receiver, instead of having volume going 1 to 10, or if you were in this is Spinal Tap, 1 to 11, it lists decibels for how loud the sound is. Well, when it's listing decibels, I usually listen to stuff at home with it set somewhere around minus 20 decibels. That can't mean the same thing as this, because I just wouldn't hear it if it was minus 20 decibels. So what is it telling me? With my sound system at home, what it's doing is taking the amplitude that I'm putting out divided by the amplitude that was recorded. So I'm 20 decibels below the recording level. And of course, how loud that really turns out depends on my speakers and other things in the room. But it gives you a way to gauge, because the difference in the decibels, well, that's what's going to be important to me. And so we'll learn about, okay, look, here's the equation we just did. We'll learn how to interpret those and then be done. So sound intensity, 0.250 meters from a roaring lion is 0.250 watts per meter squared. What is the sound intensity level in decibels? And of course, for the decibels, we're using this I0 right here. I gave you the equation, and you can do this without a calculator. If you need a calculator, go ahead. I'm not telling you don't use it, but Okay, I still have quite a few who haven't answered here. Like James, Cody, Brandy.
It's not showing.
It's not. It should be. I want to make sure you get a chance to answer because this is the last one, the whole semester. Any luck there, James? Yeah, there you go. Okay, so moving on. What we got for answers were 38, 2, 5, 0, 0, 1, 0, 4. Now, Gabriela Gutierrez, what was your answer and how did you come by that answer?
A and the calculator.
Okay, A and the calculator. So what did you put in your calculator? Just to...
What did I put in my calculator?
Yeah.
I put 10 log times 0.250 divided by 1 times 10 to the negative 12.
That is correct. Okay, now, for some reason here, my pen has stopped working again, but we have discovered that if I kill the program and start it up again, it'll work. Okay, so what she said was exactly correct, and I'm going to go through the math by hand to show you why I said you didn't need a pen for it. So you have 10 decibels times the log base 10 of 0.250 watts per meter squared over 1.00 times 10 to the minus 12 watts per meter squared. Now, just taking the number that's in my parenthesis there, that's 2.50 times 10 to the minus 1 divided by 1.00 times 10 to the minus 12. 10 to the minus 1 divided by 10 to the minus 12 is going to be 10 to the 11. So that's equal to 2.5 times 10 to the 11th. So now if I take the natural log, or it's not the natural log, the base 10 log base 10 of 2.5 times 10 to the 11th is going to be equal to log base 10 of 2.5 plus log base 10 of 10 to the 11th. One of the rules of logs is log of A times B is equal to log of A plus log of B. And so taking that, it's equal to some number. I know that it's less than 1 because 10 raised to the 1 would have been 10 plus 11. So I knew it had to be 11 point something. And my answers, you multiply by 10, so that's 110 to 120. And the only one that came between 110 and 120 was 114. So that's why you didn't need a calculator. You could do enough to narrow it down in your head. But of course, using the calculator gives us a lot more confidence usually. I think, yeah. Before I go on, I'm just going to do one problem, and that's all review from there. Before we do that one problem, important things about our perception of sound. If you have sound that's twice the intensity, it doesn't sound twice as loud at all. But if you use this equation here, and if I have sound that's twice the intensity, I'm going to have a log base 10 of 2. Right, so just to make sure it's clear what I did. If I have intensity 1 is equal to, make that a 2. Intensity 2 is equal to 2 times intensity 1. Then beta 2 is equal to 10 log of intensity 2 over intensity 0. By definition, do the substitution, that's 10 log of 2I1 over I0. Use the expansion we just saw. That's equal to 10 log of 2 plus 10 log of I1 over I0. You'll notice I don't put a base 10 when I write log. At least in physics, the standard is if you write out the word log, it's going to be base 10 unless you put something else there. I know, at least in some chemistry classes, they will write log and mean natural log, so I have to specify that. Now, if I look at this, log of 2 turns out to be roughly 3, or 0.3. 0.3 times 10 is 3, so that's 3 plus 10 log of I1 over I0. That's the definition of the intensity level that I started with. And so the intensity level goes up by 3 decibels if you have twice the intensity. Down by 3 decibels if you have 1/2 the intensity. So oftentimes, like, I don't know if you guys, I do recording at church. If you do something like that, work in the AV room, that's one of the things you always are aware of, that going up or down by 3 decibels is doubling or cutting in half the intensity. Now, to sound twice as loud, it's about 10 times more intensity. Notice that's an about. This is a human perception. It's not something that we can put exact numbers on. Some books will say 8 times. Since it's a human perception and we can't put exact numbers on, I'm more comfortable putting the 10 times because mathematically it's easier. So for something to sound twice as loud, that would be, let's say, I3 is equal to 10 I1. Doing the same work, how would beta 3 compare to beta 1? That is the intensity level when it's twice as loud compared to the base intensity level. What would I have here? I would have 10 log of 10. Log of 10 is 1. 1 times 10 is 10, exactly what he said. So if your decibel level goes up by 10 decibels, it will sound twice as loud. So that's another rule of thumb you keep in mind when you're doing audio work. If it's 10 decibels higher, it sounds 10 times louder. Okay, if this is, I said, one problem. If you have intensities from 2 different things that are mixing together, as long as they're not coherent. Coherent means you have a fixed relationship between the phases. So that means if this one's going like this one's going like this, and they have a fixed relationship, as long as you don't have that situation, which is virtually all the time, then if I have 2 sound sources, the intensity just adds. And so that allows us to do things like this here. A metal lathe in a workshop produces 90 decibel sound intensity level at a distance of 1 meter. What is the intensity level when a second identical lathe starts operating? Assume you're 1 meter away from both. If you have the second lathe, what did that do to the actual intensity? It doubled, right? That was somebody in Southwestern gave us that. So we doubled the intensity, and okay, maybe not. Double the intensity, then what does that do to our intensity level, to our number of decibels? Goes up by 3, right. So based on our rules of thumb, we can answer this one right away. A question I love, this question won't be on your final exam or I wouldn't give it to you, is if one trombone at whatever distance you are away, because you always have to specify the distance because, of course, the intensity varies with distance, produces 80 decibels, then what does, and we've all seen The Music Man, what does 76 trombones produce? How would you do that?
Take the log of 76 times 10.
Okay, 10 times log of 76 plus the beta of 1. So what's 10 times log of 76?
18.8.
So 18.8 decibels plus 80 decibels. I only have 2 significant digits here, so that's just going to be 99 decibels. So you can now understand, one trombone is this, 76 trombones is, okay. Any questions about decibel levels, sound intensity levels? The words are confusing because we have intensity measured in units of watts per meter squared. That's power per area. Intensity level is measured in decibels. So it's that word level that tells you, oh, we're doing it in decibels, not in watts per meter squared. All right, then, let us review for the exam. So I'm going to be reviewing from now until the end of class on Friday, with the exception that I'm actually going to quit in, maybe 10 minutes because we're doing the teacher evaluation. So the test will be covering chapters 1 through 17. It'll be in the lab room here at Union College. I'm not sure where it'll be over there. I don't even know the rooms at Southwestern. How would I know where it's going to be? And 1 p.m. So it's going to cover all of these things. The way I'm going to break it down is I will have, I think, 4 questions, 2 each from chapters 16 and 17. And then the other 6 questions will come from chapters 1 through 15. So it won't be 1 question per chapter. It will just be random selections from those chapters. So it's comprehensive over the semester, but with a focus on the material since the last exam. So 40% will be on the new material, 60% on previous material. So chapter 1, that's where we learned about the scientific method, basically what science is and what scientific information means, significant figures. So you should be clear on how to determine significant figures. The base units and derived units. The base units, the only units we've used all this semester were kilograms for mass, seconds for time, meters for distance, and kelvins per temperature. Those are our base units. And everything else is a derived unit based on those base units. So something like force, units of force are newtons. But newtons aren't a base unit. 1 newton is 1 kilogram meter per second squared. So you should have a handle on these units that we've used. Make sure, a lot of people still seem to be making mistakes between weight and mass. As I've been grading the most recent exams, there's still people who are saying, this weighs 70 grams. No, nothing ever weighs 70 grams because 70 grams is not a weight. It's simply a nonsense statement, right? If it's grams, it's got to be the mass. And mass is a measurement of how much stuff is present, whereas weight is a measurement of a force. Make sure you know those prefixes like we talked about so you don't have to ask, now, what does kilo mean again? Dimensional analysis is just making sure you can deal with units, have the right units in your answer, and the wonderful world of graphing, making graphs, understanding how to do that. So that's what we have from chapter 1. Chapter 2, we started doing things that were mathematical, not necessarily physics per se, but mathematical. That is, we had kinematic variables and equations for kinematics with no reason why. It's not physics per se because physics is about the reasons why. And in chapter 2, we're just saying, okay, well, if I have this acceleration and this starting speed, this starting position, I can find its ending position. That's math. It's mechanical. But you need to be able to do that because coming up, we had reasons why. So make sure you can use the kinematic equations. They'll obviously be given to you. And make your calculations based on those kinematic equations. So you'll need to make sure you can decide which equation do I need to use in this situation, what variables are important. Make sure you draw your appropriate figure showing what's happening in the problem. If I have something that is, here's the ship, or here's the Bluff of Monterey Bay Academy, and here's a ship out in the Monterey Bay. It's a very nice looking ship. And it's going to shoot a cannonball. You want to have the whole situation beginning to end of what's going to happen. And then you put in your things like, you've got this angle and you have this speed initial and you have acceleration is equal to G downward. Get everything laid out there. You probably have right? So make sure you have your figures figured out for your pictures and that you can go through and solve a problem. Chapter 3, we started talking about vectors and the fact that we have motion that can be horizontal or vertical, and the two directions are independent. That is, I can do calculations of the horizontal motion completely independently of my calculation of the vertical motion. We choose our directions. Anytime, those are vertical and horizontal, we choose vertical and horizontal for a trajectory for something flying through the air, because once it's not touching my hand, what forces are acting on it? Gravity. Now, there is also air resistance, but in this class, unless you're told to use air resistance, you assume it's not there. And so since it's just gravity, and the acceleration caused by gravity is going to be down, because that's the definition of down, then we make vertical one of our two directions, so we have an acceleration in one direction, no acceleration in the other. Makes our problem easier because acceleration being 0 in one direction is easier calculations. Make sure you can show vector addition. On the first exam, there were a lot of people that had real problems with the vector addition. And that's something that you have to be able to do when you're doing things like Newton's second law. Unit vectors are just, well, what is a vector? Vector has blank and blank.
Distance and direction.
Okay. It has magnitude and direction. If it's a vector for position, it would have distance and direction. If it's a vector for force, it would have the force magnitude and its direction. A unit vector is the same idea, except for its magnitude is 1. Hence the word unit, which means 1. So unit vectors are used to give us direction. So we define something like the x direction. We put a unit vector of x with a hat over it, and that means it has a magnitude of 1 in the x direction. So when you have independence of motion, vertical and horizontal, that's when you start doing your two-dimensional calculations. So you have projectile motion like the picture I showed here. Okay, chapter 4 and 5 were both about forces. So we call this dynamics because dynamics is studying why something happens, why we have the motion. And so for dynamics, we had Newton's 3 laws that were very important. I'll write them down here. Newton's first law says object in motion stays in motion unless acted on by a force. And I didn't say one word. A net force. Right, so if the net force is 0, an object is going to stay in constant motion, which means the acceleration is 0. So that's Newton's first law. The second law, if you know the second law, you don't need to refer to the first law because the first law tells you how the motion changes if you have a net force that's not 0. So that's the one that has the famous equation, sum of the forces is equal to mass times acceleration. Now, on exam 3, there were a lot of people who, instead of writing that, put this. That's not right. It's not right because it has to be, the net force is mass times acceleration, not any individual force. Right, so this here, and that's just wrong. There's no way to justify it. I know you'll see it in some textbooks, and it drives me crazy because it's not right. That's kind of like saying, I went to the gym and I had a plate that weighed 20 kilograms. No, you didn't. A plate weighs, 45 pounds, has a mass of 20 kilograms. We take 20 kilograms and multiply it by 9.8 meters per second squared and get what? That 196 newtons is what a plate weighs. But it doesn't weigh 20 kilograms. Okay, then Newton's third law. Newton's third law says for every action there's an equal and opposite reaction, which I can write much more simply as the force of 1 on 2 is equal to minus the force of 2 on 1. So that means if I have two objects interacting, they will put equal forces on the other, but in opposite directions. So the classic example, If I push this desk away from me, it pushes the opposite direction, so toward me, in the same force. So the force I'm putting on the desk is equal to the force the desk is putting on me, except opposite directions. That's the third law. Those are our basis for dynamics. Those are the laws that we use. Whenever you're doing something with forces, make sure you show a free body diagram. Now, what if you're doing something with torques? There's a little variation there with torques. With the free body diagram, where do you show the forces acting? All at a point. So you would put them all acting like on the center of mass of an object. But if you're dealing with torques, since torque is R cross F, you have to show the force acting where it acts. You can't show it like acting center mass. So like we had a problem on the test 3, see, I'm thinking about that a lot, that had two supports, one support here, one support here, and then it told us the weight. It's a uniform beam. If it's a uniform beam, where's the weight going to act? At the center. Well, it's always at the center of mass. And if it's uniform, the center of mass is the geometric center. So I would have the force of gravity on my beam there. There's a person out here, so you'd have the force of the person out here. And you can't forget you had the two supports, force left and force right. And you have to show the forces where they're acting. You can't show them all acting in the same place, because to do torque calculations, you have to decide what location you're going to sum the torques about, and then calculate what the vector is going from the place you're summing the torques about to where each force acts. So if you're doing something with torques, you have to not show a free body diagram, but show the breakout like this. The forces that we learned about were simply force of gravity. We learned force of gravity two different ways. One with the force of gravity is equal to mg. That applies if you're on the surface of the Earth, where the radius from the center of the Earth to the object is the radius of the Earth, and the mass of the thing that's attracting is the mass of the Earth. In that case, we use g, which is 9.80 meters per second squared. That's an average value over the surface of the Earth. It does vary. If you go to the equator, you're going to be farther away, the radius is bigger, and the g is smaller. If you go to the poles, you're closer to the center of the Earth, and g is actually bigger. So it does vary, but we just use an average value for our calculations. If you're not on the surface of the Earth, or you want to be more exact, then the force of gravity you use has force of gravity is equal to capital G, mass 1, mass 2, over r squared, always in the attractive direction. So if I were to take me and Paris, the force of gravity acting on me is pulling me toward Paris, with the force of g, that constant, which of course would be given, times my mass, times Paris's mass, and divided by our separation squared. And on Paris, what direction is the force I'm putting on Paris? It's the opposite direction coming toward me, because Newton's third law says that they have to be equal and opposite. Then we had friction. Make sure you know the difference in static friction and kinetic friction. The static friction is always less than or equal to the maximum value of coefficient of friction times force normal. The kinetic friction is always equal to coefficient kinetic friction times force normal. So kinetic friction is the easier one because it's got an equal sign. Most of our problems, we simply say at the limit, which means we're going to use an equal sign for the static. That brings us to normal force. Be clear on the direction of normal. Right? There are still people who say normal is up. Normal is up if you're looking at your tabletop. Normal is not up if you're looking at the wall. So make sure you're clear on what direction normal is, the point of the normal force to keep something from going through the object until it breaks. Then we have the spring force and the tension force. I think we're clear on those. Stress and strain, we had three different types of stress. Compressive, which is forces pushing into the surface. Tensile, forces pulling out of the surface. And shear, forces parallel to the surface. At this point, I'm going to stop because we're doing the teacher evaluation. You should have all received an email. You can also simply go to Moodle. And on Moodle, up here at the top, depending on which class you're in, you only see one of these three things. But you have the teacher evaluation for Physics 151 if you're in the 151 class, 251 if you're in the 251 class, or if you're Southwest, it says Southwestern Baptist University Physics 151. So go there on your computer, your smartphone, whatever, and fill out the teacher evaluation. And I will simply, granted I can't look over your shoulder